Talk about linear approximation. So at the top of the page here, you can see a reminder of our kind of fancy rearrangement of a tangent line formula. So for this section, we're going to use a tangent line is L of x equals f of a plus f prime of a x minus a. So this is for the tangent line to a function f of x at the number a. So this will be the y value at that point. This a over here is the x value of the point. And then right here, we have the derivative at that point. This x stays the letter x and is actually the input to the line equation when you're done. All right, so in the problems in this section, there's a lot of vocab that's equivalent. So you can see in this first example we'll do, it says to build a tangent line to a function. We may see this same problem set up, but they say build the linear approximation to this function. That would be the exact same problem. They're just using different language. Or they could say the local linearization of that function. Again, same thing, just alternate language. Okay, so this first example, we're going to build the tangent line to e to the 4x at 0. And then we have a follow-up like part B here, use it to estimate e to the 0.04. So we'll ignore the 0.04 part for a while and just start with the tangent line to this function. So for this tangent line, I need f of 0 and f prime of 0. So f of 0, I'm going to just plug 0 into this function. That's e to the 0, which is 1. So this 1 is the y value that starts off this formula. I need to compute the derivative of the function and then plug in 1 to get f prime of, or sorry, 0 to get f prime of 0. E to the 4x's derivative is a chain rule where the outer function is e to the x, the inner function is the 4x. So our derivative comes out e to the 4x times 4. Now, if we plug our number 0 into that, we get e to the 0 times 4, which is 1 times 4 is 4. Okay, so this is all the information I need to answer the first part of the question to build the tangent line. So I'm going to say L of x, the line, is the y value plus the derivative times x minus the x value. So 1 plus 4 times x minus 0. You can leave it in this format because this number happens to be 0. We could also just write this as 1 plus 4x, and it's just slightly cleaned up, but both of those are correct. Okay, so for the second half of the question, we want to use this line to estimate the value of e to the 0.04, essentially without a calculator. So we want to start by deciding what number has been plugged into this function to give us e to the 0.04. So because the 4 is part of the original function, this is actually f of 0.01, right? If I plug that number in for x up here, I'll have e to the 0.04. So this is f of 0.01, which can be approximated by L of 0.01. Which makes sense as well because we built the tangent line at 0. So it would only make sense for it to estimate at x values very close to 0, such as 0.01. All right, so now I'm going to plug 0.01 into this formula. That's 1 plus 4 times 0.01, 1 plus 0.04. So we get 1.04 as our answer for that second question. If we want, we can actually check in a calculator how close to the right value that is. So we would do e to the 0.04 power. We get 1.04 and change. So this approximation we did with no calculator is actually pretty good. It's correct to a couple of decimal places. All right, let's try our second and final example for this video, which is kind of the other setup for problems in this section. This has a lot less information in the instructions, but it is the same type of problem. So this just says, use a linear approximation to estimate 0.99 to the 5th power. Right, so the key here, before we jump into computations, is to see how it is the same setup as this previous problem. So we want to build a tangent line to some function at a nice number, and then use it to estimate the function with a less nice number in it. So we want to build a tangent line to f of x equals something at some particular x value or a value, and then estimate f of a tougher number. All right, so for the function itself, it's going to be the operation here. So the raising to the fifth power is the operation. So I decide that the function would be x to the fifth. And I want to build a tangent line. I have to do this by hand, no calculator. So the number I choose for this tangent line has to be ideally an integer, if not some other really, really nice number that I can work with. So I just want to pick the integer that's closest to the bad number. So we have 0.99. I'm just going to choose x equals 1, which is really close to it, but much easier to do these tangent line computations with. Then for the second part of the question, I can estimate f of 0.99, right? Then it is a very close number to where we built the tangent line, but f of 0.99 would be 0.99 to the fifth, which is the goal of the problem. Okay, so once I have this all established, I'll tackle this very similar to the one above. I'll need f of 1, which is 1. I'll need the derivative of the function, that's 5x to the 4th. Remember, my f of x is this x to the 5th. So f prime of 1 is 5 times 1 to the 4th is 5. That makes our tangent line y value plus derivative x minus x value. Okay, so now I'm going to take this 0.99 to the 5th that I want to estimate, which we said is f of 0.99. And we're going to estimate it with L of 0.99 because this, we technically could do this by hand, but it would be very annoying. The one above, we had no option to do it by hand. But if we do it by hand with the straight line, it's a lot easier of a computation. This is 1 plus 5 times 0.99 minus 1. That gives me 1 plus 5 times negative 0.01. 1 minus 0.05, which gives us 0.95. And again, if we want to check how close our answer is to correct, we can come back to the calculator and say 0.99 to the fifth power. Sure enough, 0.95 and change. This is actually not a bad estimate at all, especially not having had a calculator.